Well, you need the 800 bags of heroin as well. I'm so excited for today's conversation. We are joined by Professor Mark Colyvan from the University of Sydney. Mark, welcome to Increments.
Thanks for inviting me. Great to be here.
Yeah, so perhaps just to set up this conversation a little bit for our audience. So you have done a lot of work in the philosophy of mathematics, and I have only recently learned how interesting this field is. And in particular, you've done a lot of work talking about the nature of mathematical explanation. And our audience is very interested in just the nature of explanation, both scientific and mathematical. And so I thought it would just be a great opportunity to get to chat with you about the various things you've been thinking about and help us start thinking a bit more clearly about how mathematical explanation works. So perhaps we can start by just a quick introduction, telling us a bit about your background and the kind of problems you're thinking about these days.
Well, I'm a refugee from mathematics, so I started out doing mathematics, as is not uncommon in philosophy. A lot of people working in the technical ends of philosophy, logic, philosophy of mathematics, philosophy of science and the like often come from the sciences. So I came from mathematics and then defected across to the dark side and did philosophy for my PhD and worked on philosophy of mathematics. And I tend to work on the mathematical end of philosophy generally, working in decision theory, logic, philosophy of mathematics, mathematical applications in science. So I do a bit of work in ecology and conservation biology. So wherever mathematics arises, I tend to get interested. And so philosophy, of mathematics is an obvious place for people like me to spend their time. So I'm not sure how much you want to hear about philosophy of mathematics in general, but it's just, as is the case with philosophy of anything, it's looking at the philosophical issues or sometimes the meta issues about the subject. So if you're doing philosophy of physics, you're not actually doing the physics, although you've got to be on top of the relevant physics. You tend to be looking at philosophical interpretations of quantum theories or the like. And so too with philosophy of mathematics. There are lots of questions about mathematics that are not entirely mathematical in their nature. So, for instance, the issues about explanation, one of the things I've always found really interesting is that mathematicians will talk about explanation within mathematics, but without giving clear idea of what that amounts to, without having a theory of explanation. And why should they? A theory of explanation is not something that's sort of within the mathematicians' tool bag, as it were. So they have clear ideas about when bits of mathematics are explaining other bits of mathematics, when a proof is explanatory, and so on and so forth. But what's going on in those particular cases? What are they talking about? What is the notion of explanation? These are all philosophical questions. And it's one of the reasons, I should say, that I kind of defected from mathematics to philosophy, because I got interested in these things and fortunately for me, found that there was a discipline that addressed these questions. How is it that mathematics gets applied to the physical world? This a priori enterprise of mathematics, largely a priori, turns out to be exactly what we need to do physical sciences. That's always intrigued me, and thought that if I just did more mathematics, I would understand that. And then somewhere along the line, I realised that this was something that these questions were arising in the boundary between mathematics and philosophy. So that's how I ended up becoming a philosopher.
Excellent. Yes. To follow up on that, I think some people may have read or at least heard of the famous essay, "The Unreasonable Effectiveness of Mathematics," and that kind of touches on the last part of your comments about why are these squiggles that we write on paper that seem to abide by certain rules, why are they just so indispensable for the project of both science but also just figuring out the world around us? Why do they seem to be required by so many different fields? And I think that's going to maybe encroach a bit closer to the question of the role of explanation in answering that, but maybe as a bridge from some questions that presumably our listeners will be somewhat familiar with to perhaps some questions that they won't be familiar with. We could start by tackling or discussing the question of the unreasonable effectiveness of mathematics, which I believe is chapter 6 of your excellent book, An Introduction to the Philosophy of Mathematics. So what are your thoughts there?
Yeah, I mean, it's one of the great puzzles, I think, about mathematics is if you were to play the role of sociologist and sort of go into a mathematics department and look what they do. I mean, nowadays there's a lot more computers and a lot more modern techniques, but traditionally what you would find in a mathematics department is a bunch of people sitting around with pencil and paper and thinking and proving things on paper. Very little interest in the outside world. Again, that has changed a little bit, I think, in recent times, but traditionally sort of pure mathematics was something entirely a priori, just prior to any evidence, not looking at the world, not interested in the way of the world. You don't look for counterexamples to theorems by looking at the world. You look for counterexamples by looking at the mathematics. And then it turns out that this is precisely what you need to do general relativity, for instance. And that has always just intrigued me. It should be the other way around. Natural way of thinking about it is when Einstein is playing around with requiring non-Euclidean geometries for general relativity, you would think that Einstein would walk over to the mathematics department and say, "Can you guys work on this, please?" And instead what he finds, he walks over there and they say, "Hey, we already did this. You've got an application for this? Wow. How cool, It just seems the wrong way around. And has always intrigued me. Now, I wish I had a story to tell about how that works, but Eugene Wigner, in his famous essay on the unreasonable effectiveness of mathematics, I think just raised this issue beautifully. And was not really taken up by philosophers of mathematics for quite some time, and this always puzzled me, and I actually did a little bit of searching around to find why don't people get interested in this topic. Maybe I'm missing something. Maybe there's a kind of clear answer and Wigner was just confused. So I thought maybe there was an answer out there somewhere. So I went looking, and there are various articles suggesting partial answers about what's going on. But philosophers, by and large, just didn't really take up the challenge here. And this kind of puzzled me. So one exception being fantastic work by Mark Steiner, has written a series of articles and a book on this topic. And that really gave me heart. I thought, okay, so finally someone gets it. I'm not alone here in thinking that this is a puzzle. So what's the answer to the puzzle? Like lots of philosophers, I think that just appreciating the puzzle is at least some progress, and that's really the only progress I can claim here, is that I do think that Wigner got at something really important about the applications of mathematics in science, and trying to understand that relationship, I think, for me, is the core of what you might think of a philosophy of applied mathematics.
Nice, yeah. I want to return to something you mentioned briefly when you alluded to just like your approach to these problems. So in your book, An Introduction to the Philosophy of Mathematics, you mentioned that philosophy, or at least your approach to these questions, is to look at what's happening in the field of mathematics and then base the philosophy around that. So you get the problems from what's going on in the mathematics community, and you get your puzzles from sort of these like real world problems that you're faced with, instead of sort of developing your philosophy and then trying to force this on to the way people do math. And so I'm just curious about your approach here to the philosophy of mathematics, and whether this differs from some of your colleagues, and sort of how you came to approach mathematics in this way. Your philosophy of doing the philosophy of mathematics, if you will. Yeah.
Right, good. We're already doing philosophy of philosophy. That's this happens very easily when you're talking to philosophers. So it's nothing particularly original to me. I mean, this is an approach used by, in my book, most good philosophers will take this kind of approach, that if you're doing philosophy of science, you don't sit in judgment of science back in your armchair doing philosophy and saying, oh, yes, that's good science. No, that's not, whatever. The role of the philosopher is not sort of ultimate arbiter in these matters, but rather a co-worker. So you work sort of, the metaphor is, philosophy is continuous with the science, and that you have different expertise. So my expertise in philosophy includes a lot more logic, for instance, than most mathematicians will have. It includes, obvious expertise in philosophy itself, but also philosophers very often have an overview of things. So we're often jacks of all trades. I know a little bit of physics, I know a little bit of conservation biology, I know a little bit of ecology, I know a bit of mathematics, and I know a fair bit of logic, and sometimes that can be helpful. But the idea that philosophy, sometimes it's pejoratively talked about as first philosophy. Philosophy comes first, and then comes science. But philosophy is the ruler here. And the modern approach, I think, to philosophy, particularly a philosophy of sciences and mathematics, sometimes goes by the name of naturalism, after the work of Quine. And the idea here is that philosophy is continuous with science. You're working shoulder to shoulder with scientists, and you can criticize science, but you do it sort of from within, as it were. You don't sort of sit back and say, "Oh, my philosophical theory says that this can't be right, so back to the drawing boards and get back to me when you've got something new." Of course, that's a caricature. I'm not sure in the history of philosophy anyone's done exactly that, but you can find things heading in that direction at various points in philosophy, whereas the approach that I think most naturalistic philosophers at least would take is, okay, here's my critique of what's going on, and it's it's fallible and the like, just like the rest of science.
Mm-hmm. Nice. So there's no philosopher kings in the philosophy of mathematics.
No, unfortunately, I wouldn't mind that job if there were one going, but.
So yeah, let's get into some of the details. So first, maybe the most basic question is just, what is an explanation? How do we start thinking about explanations as contrast to other, say, forms of description or forms of argument or forms of proof? Let's start from the basics and start building on that.
Well, it sounds like the basics, but it's not. Right there, you've got some really big questions. So one of the problems about the philosophy of mathematics and explanation there is that there's no agreed upon account of what explanation is anywhere. And so if we're talking about explanation in, just take a science generally, an explanation usually can think of it as an answer to a why question. You say, why did the billiard ball go into the corner pocket? And then you say, well, because it was hit by the cue ball in such and such a way. And then you're going to do a little bit of talk about vectors and momentum and so on and so forth. But you can give an explanation for why the cue ball ended up why the ball ended up in the corner pocket in terms of explaining its causal history, for instance. That's a very common form of explanation, where you say such and such event occurred, and the event occurred because, and then you trace back and say something about the causal history. And that pushes the lump in the rug elsewhere, but it doesn't actually help that much, because now we want to know what causal histories are. What is causation? A notoriously difficult problem in history of philosophy and philosophy of science. But, set that aside for the moment, but that is a pretty big lump in the carpet to be pushing around. But that's one style of argument, is that you've got an event and you trace its causal history, and now we know what's going on. That's not always going to be exactly what you're after, though. For instance, sometimes tracing out the causal history doesn't help understand what's actually going on. So, for instance, if there's some universal law there that's the reason for something occurring, then just telling me about the actual causal history of this particular thing doesn't help. So, for instance, if I've got a spinning top and it stops spinning and then it falls over, right? Why did it fall over is the question. Well, I'm going to tell a story about conservation of angular momentum. That's why it stays up. In fact, that's the kind of odd state, the fact that it's staying up. That it should fall over is because it's in an unstable configuration when it's not spinning. Okay? But the causal history there would be something like it was hit by a particularly large... Let's suppose it was perfectly balanced at the point that it stopped spinning, or the angular momentum was low enough that it was no longer holding it stable. Then the actual causal history would be something like it was hit by a particularly energetic air molecule from this particular direction, which pushed it over that particular way. That's the causal history, but what you really want to know is that it's unstable. If it wasn't that air molecule, it would have been some other. And in fact, it doesn't really matter which air molecule in which direction. What you want to know is why it fell over. And that's going to be a story about stability. It was in an unstable configuration when it's not spinning. When it's spinning, it's fine because of the conservation of angular momentum. So there's a sort of... Already the alarm bells should be ringing if you think that it's just about the causal history. Sometimes it looks like either you're going to need an enriched notion of what causal history is to include talk about stability and general laws, or at the very least we need to be careful about what you mean by causal history as an explanation. But there's a sort of fairly mundane case where I think the narrow causal history view is not giving you the information you want. Why did the top fall over? So what is an explanation? Sometimes it's causal history. It also seems to be closely related with counterfactuals. So counterfactuals of the form, if such and such had not occurred, then this would not have occurred. So, for instance, an example like, why did the window break? It was because it was hit, someone threw a rock at it. And what you want to say there, here's the test of whether that's really the explanation, is had the rock not been thrown, the window wouldn't have broken. So that counterfactual is testament to, in a way, to the fact that the rock is in fact the right explanation for the breaking of the window. So these are counterfactuals are closely tied to explanation. Some people have a counterfactual account of what explanation is. That's all there is to an explanation. It is just supporting these counterfactuals, and a number of different theories. I won't go through them all. Another, just quickly, is it's something about conservation of certain quantities. So in the billiard ball case, you can talk about conservation of momentum. It's momentum transfer from one ball to another, and with suitable vector analysis, that's why it ended up in the corner pocket. So it's not merely the causal history, but the causal history, if you like, is spelled out by some conserved quantities, whether it be charge in electromagnetic cases, angular momentum in the top case, so on and so forth. So it'll be some quantity, that's physical quantity, that's conserved. And that's another theory. So there are a number of different theories about what explanation is in science. Arguably, the folk notion, kind of the everyday notion we use of explanation, is some kind of mishmash of all of these, I think. And so, to mathematics, what's the correct account of explanation in mathematics? Well, it turns out to be even more difficult still, because, in my view, none of those work. So whatever your favourite candidate is elsewhere, and the problem there is there's too many of them, and none of them seem to be exactly right, but they're in the ballpark. None of them seem to be even starters for mathematical explanation. So if I perhaps say what I take a mathematical explanation to be, it's when a mathematician says something like, this proof tells me that the theorem is true, and this other proof tells me both that it is true and why it is true. So this proof is explanatory. So these are two proofs of the one theorem. One proof will tell me why the theorem holds. The other will tell me merely that it holds. So explanatory proofs are greatly valued in mathematics. Now, we'll perhaps later we can talk about whether explanation can live in other places other than proofs, but just setting that aside for the moment, it seems that there is this distinction in mathematics between explanatory proofs and non-explanatory proofs. And it makes sense. This proof just kind of convinced me that the theorem is true, but I'm none the wiser as to why it is, just that it is, right? And another proof enlightens me in some sense. What's that got to do? There's no conserved quantities. It's not like preservation of angular momentum is, running through the explanatory proof. Mathematics isn't really even a causal discipline, so looking at causes seems like a category mistake. Counterfactual dependence. Had this mathematical fact not held, then this other mathematical fact wouldn't have held. If you say it quickly enough, that sounds like it's heading in the right direction. But just think for a moment about the first part. If this mathematical fact had not held, mathematics is supposed to hold of necessity, right?
Right.
How can something that's necessarily true be not? So, spell it out with a particular example. If 17 weren't prime, then how on earth do you finish that sentence, right? So counterfactuals just don't work in mathematics. And yet the standard story about explanation is that at least it's closely associated with these counterfactuals. And it's really hard to get any sort of counterfactual that even sounds like it makes sense when you're talking about mathematics. For what it's worth, I've been playing around with that. I can maybe talk a little bit about that later. But just to sort of appreciate the problem for the moment, that's really hard to make sense of a counterfactual when the things that you're talking about are necessarily true.
Just to follow up on to test my intuitions here a little bit. So when I think about counterfactuals in mathematics, I think that's going to have something to say about the axioms. So an example that comes to mind is something like, suppose the angles of a triangle don't add up to 180 degrees. Well, the counterfactual there would take us into the land of non-Euclidean geometry.
Right.
And so presumably it was questions of this sort which then got people to think about the fundamental axioms upon which their theory is based and start questioning alternatives to that. And so does that count as a counterfactual in mathematics, or is something going on there that's something extra, something else that I'm missing?
Right. So if you can make sense of a triangle in a non-Euclidean space, and just to note here, it's not trivial, right? We can make sense of triangles in non-Euclidean spaces. So on the surface of the Earth, you can follow the equator around and two different lines of longitude, and then you've got three angles. You've got the angle at the pole, and you've got the angles at the equator. So you've got three angles, so it's a triangle, right? And the lines, what you mean by lines here, are going to be great circles, right? But notice what we have to do is we have to generalize what we mean by line. Okay, so we start with the Euclidean space and we say, what is a line? Well, it's straight. It has zero curvature, right? No, that's a bad way to define a line if you want to generalize it in that way, right? What you want to say is it's the shortest distance between 2 points, and that's what really matters. Okay, so take that as your definition now, and of course great circles then become lines. No, but if you had taken something to do with curvature as your kind of your starting point, or something you can draw with a ruler, right? That would also be a natural definition from primary or high school. So you've got to get the right core notion of what a line is in order to generalize it to non-Euclidean spaces. triangle then becomes straightforward because it's just something with these, the generalized notion of line that has three angles. And so the equator with two different lines of longitude counts as a triangle, and the sum there is greater than 180 degrees. So you're right. You might think that that's what's going on when you think about counterfactuals in mathematics. Is had the rules been differently, had been different other than the way they are, or had we had different axioms? But then there's a concern that you're changing the subject. So, for instance, if I say, if I'm talking about a group in group theory, and if I say, what if the identity element were not unique, right? And for those who don't know this, that's a theorem of group theory, that the identity element is unique. It's one of the first things you prove in group theory when you're learning this, right? Then what are you suggesting there? What are the changes to the axioms you would require to get that? It's not clear exactly what they would be, but presumably there is some change of axioms that would allow that. But then what you're inclined to say is, well, that's not a group, right? A group is a thing, is defined by the group axioms. So what you're saying is, suppose I had some other algebraic system defined by a different set of axioms, and in that system, the identity, you guys got to scare quotes around everything now, right? The identity element is non-unique. There's a good case to be made, at least, to say, no, that's not a counterfactual. You're just talking about something else. Whereas if I say, suppose I had slept in this morning, I wouldn't be talking to you now, right? There's no question about my identity in that, right? You can't say, well, if you'd slept in this morning, that's kind of such a aberration in your character that would not be Mark Colyvan. That would be someone else we'd be talking to then, or not talking to, as the case may be. No, that's just, you can stipulate things like that. Had I slept in, even if it is out of character, it's still me we're talking about.
There's no axiom of sleep here. You're not. You wouldn't be breaking any of the axioms of the system, or to beg that question.
Yeah, and if you think about actual cases like had 17 not been prime, what axioms do you need to change there? Will you change the Peano-Dedekind axioms of number theory?
Right.
But then those axioms are not just arbitrary axioms that are sort of thrown together. They're supposed to capture the nature of natural numbers. And so it's kind of not clear what you're doing there. It's not like slipping from Euclidean to non-Euclidean geometry, which are two perfectly good geometries. There really is only one story about the natural numbers. And it would be very, very odd to say, if 17 weren't prime. And as soon as you say that, the almost immediate reaction you get from someone, and I've uttered that phrase more than I should care to admit because I'm interested in these counterfactuals, right? If 17 weren't prime, people just jump on you and say, you're not talking about 17 anymore. If 17 weren't prime, then you're talking about 18 or 16 or something nearby maybe, but you're not talking about 17 because it's of the very nature of 17 that it be prime. So these are the kinds of problems. Yes, you might be able to make sense of some counterfactuals, like if the angle sum of the triangles had been greater than 180 degrees, then we're now talking about non-Euclidean geometries. But you can also create problematic cases even there. You say, suppose in Euclidean geometry the angle sum of a triangle were not 180 degrees. What would that mean for Pythagoras' theorem, right? Okay, now we're stipulating that we're in Euclidean geometry and we'll get the same kind of problem. So you're right. I think there are ways of making sense of some of these counterfactuals by adjusting the axioms, but I think there are plenty of cases where that's just not the case.
So it seems like in the triangle case, to make the counterfactual statement even make sense, you're sort of unknowingly appealing to a more abstract axiomatic system that can capture Euclidean geometry under certain assumptions, but that's only like a special case of sort of a more abstract, more general set of axioms. And so when you're asking the question, like, suppose the angles of a triangle didn't add up to 180, unbeknownst to you, you're actually appealing to this like more abstract axiomatic system, but you just kind of don't know it. Whereas in the natural numbers case, axiom 17 isn't prime. Like, there's sort of no, or as far as we know right now, it's like there's no more abstract axiomatic system that you can kind of be appealing to. Is that coherent at all?
Yeah, I think something like that is right. I think that even if so the first person to sort of ponder about, wonder whether whether you could have triangles whose sum did not add up to 180 degrees, despite the proof that they did, right, in Euclidean geometry. You said, but what if they didn't? What would that mean for the rest of geometry? Then they're not sort of latching on to non-Euclidean geometries right there, but they're just, open-minded about it, and it turns out that there is a way of making sense of that, unbeknownst to the first person, at least, whoever pondered that. Whereas in number theory, maybe there is some sort of strange other number theory, but it's very odd to think of it as the theory of the natural numbers, right? We have a very definite thing in mind when we think about the natural numbers. There are other algebraic systems, right, that have some of the features of the natural numbers, but they're not the natural numbers, right? So when you want to say if 17 and thump the table, and I mean 17, if 17, that very thing, were not prime, you still get people saying, well, it ain't 17. Right? Whereas if I say, had I slept in this morning, you don't find people saying, well, that wouldn't be you, that would be someone else. No, I've said it was me, right? So that seems to be a big difference. Trying to make sense of counterfactuals in mathematics is problematic, and that's, given the close relationship between counterfactuals and explanation, that's part of the trouble. And you might think that you need counterfactuals anyway, setting aside explanation. One of the things that mathematicians do is look at ways things might be under certain assumptions. So open questions in mathematics, like the Riemann hypothesis, the details of it needn't concern us, just that it's an open question in mathematics. There are mathematicians working on both sides of that. If the Riemann hypothesis turns out to be true, then what's that tell us about distribution of primes? If it turns out to be false, what does that tell us about the distribution of primes? One of those is impossible, right? The Riemann hypothesis is either necessarily true or necessarily false. And so one group of those mathematicians are engaged in what are known in philosophy circles as counterpossibles. They're not counterfactuals, they're counterpossibles. They're looking at any possible antecedent and looking at the consequences of that. And they don't know which group of mathematicians are doing that, but one of them surely is, because the Riemann hypothesis is either necessarily true or necessarily false. And so a lot of work in mathematics is like that, because let's suppose I don't know the answer to this question, but suppose this theorem turns out to be true, then let's prove another theorem from that, right? But you don't know whether it's true yet. So you're engaging this kind of counterpossible talk, I think, rather commonly in mathematics, independent of anything to do with explanation.
Yeah, it's so fascinating because so a couple examples kind of leapt to my mind to highlight the distinction between counterfactuals and counterpossibles. So the imaginary numbers, you could imagine someone saying, suppose it was true that the square root of -1 was defined, then what comes of that? And what's so interesting about counterfactuals in mathematics is you can then just start making it factual. You could take something that's counterfactual in some cases and now make it factual through definitions and start building on top of certain axiomatizations and build out entirely new branches of mathematics just through asking such questions. But that isn't the case always. It's not the case with the 17, for example. It doesn't seem to be possible to make an alternative even possible at all. And so I would love to go into the nature of impossibility, if that's not too grandiose. And I know that you've written some stuff about the role of explanations which invoke the impossible. And so how do you think about the impossible in explanation and in mathematics?
Well, this is sort of closely related to this. Obviously, if you're looking at counter possibles, you've got to look at situations that are not possible, but in some sense are imaginable or something like that, right? And the usual account of counterfactuals involve possible worlds, right? You move to another possible world where things are thus and so, and then you look at what would happen in that world, right? This is sort of philosophical jargon, but it turns out to be extremely useful to think of it in these ways. So the world in which I slept in this morning is not this world, because I didn't, but some other nearby world as much like this world as we can. We don't want to change the laws of physics and the like, because after all we require is for me to sleep in. So you just change that fact in this world, but it's not this world anymore because I've changed that fact. So I've got another possible world, and I don't have to break the laws of physics or the laws of logic for me to sleep in. Sadly, it happens often enough, but we don't have to change too much to get that to occur. And then we sort of look at, well, what would have happened? What goes on in that world is the way to think of it. So, if I was scheduled to have a discussion with you guys this morning and I slept in past a certain point, then either discussion would be delayed or we would cancel and reschedule, whatever, we can very easily see. So it doesn't require any, mysterious occult abilities to look into these other possible worlds. You just stipulate this other possible world is thus and so. And in order for that world to be a consistent world, what else would need to happen? Well, obviously, the discussion would be delayed or something like that. Mm-hmm. So you can sort of see what would happen. That's the way we assess counterfactuals. There's a formal semantic theory of how this goes on. We didn't go into that. But when you're looking at counter possibles, there are no possible worlds in which the impossible happens. So you need to enrich this theory, and there are such enrichments invoking impossible worlds, and there are ways to go about doing that. But it stretches the mind a little bit more when you start thinking about the impossible. But just to give another mathematical example, so the example of the extension to the complex numbers is a good one, because at first brush you think square root of -1 makes no sense, right? Why not? Why? What's wrong with that? Well, it's by definition that multiply two numbers together. If they're both positive, then the answer is positive. If they're both negative, the answer is positive. So there's no such thing as a square root of a negative number, right? That's a good argument. There's just no room there for there to be such a thing. But what you do is you stipulate that there is such a thing and hope that you don't get into trouble. Hope that you're not stipulating something that actually undermines other things that you've got going on, right? And it turns out one of the reasons we accept complex numbers is that it turns out to be a beautiful generalization of all sorts of things. Not only does it not undermine anything, it helps us make sense of trigonometry, for instance, understanding the relationship between complex exponentiation and trig functions, for instance. So it helps sort of unify, brings everything together. So it does the exact opposite of some undermining stuff. It actually turns out to be that's what we needed all along. And why should we believe now in square root of -1? Well, because of its applications. That's the ultimate answer here, I think. It's not that we've got a proof that it exists, because we just stipulate that it exists. It looks like it's incoherent on the face of it, but it turns out to be extraordinarily useful. Think of other cases, though, where we've got something that looks like it doesn't make sense. So I'm not sure if you're familiar with non-standard analysis. Right. Okay, so in non-standard analysis, one way of putting it, in non-standard analysis, you're trying to make sense of the calculus as conceived by Leibniz and Newton, where they had these things called infinitesimals. Modern calculus dispenses with them, or we still talk about that way. We still say infinitesimally close to such and such. Right. And what we really mean by that, if you push me on that, is I'll give you some fancy limit talk in terms of epsilon and delta, right? But I get rid of all those sort of infinitesimals. I don't believe in little infinitesimals, right? Mm-hmm. But in Newton and Leibniz, you've got these quantities, right? They behaved like zero when you wanted them to, and they behaved like something really, really a real small real number, something close to zero but not zero when you wanted them to. So in particular, when you're dividing by infinitesimals, you can divide by them perfectly fine. So they're not zero because you can't divide by zero. But when you've got some expression plus an infinitesimal, you just drop the infinitesimal off and write equals at the next line, which is to say that the infinitesimal was, in fact, zero after all. But the line before that, you divided by the damn thing, right? So they're both zero and not zero. And indeed, Newton and Leibniz were criticised by the philosopher Berkeley for this very point, right? It's an inconsistent theory. Calculus is inconsistent in its early days, and for quite a long time afterwards. I don't think it was until the middle of the 19th century, work of Weierstrass and others, that we finally got the modern notion of limits and were able to tidy it up. So what you've got here is a theory that's straightforwardly inconsistent. I think Berkeley was right. What's the response of those using calculus? Well, it works. It's right. Really, really useful. Inconsistent though it may be, we just need to be pretty careful about these infinitesimals. And there were sort of rules governing the way you use them, so you didn't do things like, delta x equals zero and delta x doesn't equal zero, so zero is not equal to zero and all hell breaks loose, right? You're careful not to do that sort of stuff. But you're flirting with inconsistency in these cases, and it turns out later on it can be tidied up with fancy limit talk with epsilon delta notation of continuity and the like. But back to non-standard analysis. Non-standard analysis is a way of trying to make sense of those original notion of infinitesimals. And so what you do, in effect, is you stipulate that you've got some number that is greater than zero but smaller than every real number. Sorry, smaller than every positive real number, right? So there's...
Okay, right.
So it's smaller than every positive real number, but it's greater than zero, right? And again, intuitive, you think there's no room there, right? Right, there's no gap between zero and the positive reals. But you just stipulate that there is. Huh. And then you give some rules for understanding these things, and turns out you can build a model of these things. You can build a model of these infinitesimal quantities, and it's a perfectly good way to do calculus. And some people will say, well, that's the kind of thing that Newton and Leibniz had in mind all along. And maybe that's right. But again, it's flirting with inconsistency, right? It turns out you can build a model of this, so it is in fact consistent. Non-standard analysis, I'm not saying it's inconsistent, but the original idea, I think, was inconsistent. And here we've got now two different ways of making it kosher. Sort of the standard calculus approach via limits, and a non-standard approach by introducing infinitesimals and appropriate rules governing their behaviour. So I think this kind of thing goes on, perhaps not all the time in mathematics, but happens often enough where you're flirting with something that looks like it's inconsistent, or in fact maybe even is inconsistent, and it's tidied up later. But that doesn't change the fact that while you're flirting with it, it's not. There's no known way of tidying it up, right? Other famous examples, set theory, when early days of modern set theory, right? You're provably inconsistent, but still, set theory went on for another 20 years, pretty much as it was, without leading to too much trouble. You just had to be careful that you didn't mess around with the set of all sets and the Russell set, and we knew where the dangers were, and we avoided them. But it's not to say that set theory was consistent. And indeed, we still don't have a consistency proof of set theory.
So one of the things I found so interesting in your book is there was a panic about the whole inconsistency of set theory at the beginning of the 20th century, if I recall. But you make the point that unbeknownst to mathematicians, they had been working with an inconsistent calculus for ages, and the sky didn't collapse and nothing terrible or calamitous happened. And what do we do with that? Is the requirement of consistency in mathematics a reasonable one, or is your example of the unbeknownst inconsistencies that Leibniz and Newton introduced perhaps a reason to think that consistency isn't so required after all?
A good question. I think that consistency is a good thing. It's hard to argue with it. You'd like your theory to be consistent. Yeah. But the problem is, thanks to work of Gödel, we know that there are trade-offs here, right? So Gödel's incompleteness theorems tell us that if the system is consistent, if you've got a system, a formal system, we're going to need to qualify this appropriately, but if you've got a formal system rich enough to do basic arithmetic in, then if it's consistent, it can't prove its own consistency, right? So what you've got here is a trade-off between consistency and the expressive power, if you like, of the thing. It's not able to do what you would like it to do. So do you want to settle on the consistency? Because if you've got an inconsistent system, you can do these sorts of things, right? So, and there are people playing around with explicitly inconsistent mathematical systems. And one of the virtues of these systems is, apart from anything else, they have some greater expressive capabilities. But, for the most part, we would like to have consistent systems. But the price you pay for that is that you can never prove from within the system. There's other things you can do to convince people that the system is consistent, but you can't prove from within the system, if it's an interesting enough system for mathematicians to be playing with, you can't prove within that system that it's consistent. And that's a serious limitation, and there's no way around that. So if you really value a consistency, you would like there to be a proof. Whereas what we have with set theory at the moment is that we've looked really hard and we can't find any inconsistencies. That's an odd thing for a mathematician to settle for, when you think that mathematicians will require proofs of anything before they're willing to believe it. Right? Even if you say you give them inductive, not mathematical inductive evidence, but scientific inductive evidence. We've checked this for all numbers up to 10 to the 10, and it seems to hold for all of those. Well, they say, well, that's not a proof. Could be the next one and doesn't, right? And that's exactly right. But to say that, why do we believe that set theory is consistent? Because we've looked really hard and we can't find any inconsistencies. And in particular, we can't find any inconsistencies in the ways that it fell over last time with naive set theory. And it turns out, in a way, that's as good as we can get here. So I'm not criticising this. I'm just, stating that that's what we live with set theory. We hope that it's consistent. We believe that it's consistent because it's held up for 100 years or so.
So the reason I think this is so fascinating is mathematics is often heralded as the domain of perfect truth. And so in science, we recognize that we're always fallible. In science, we recognize that any theory could be wrong, and that's as best we can do in science. But in mathematics, that's not the case. So the popular conception goes. And so what I just think is so fascinating is that it is just so much the case in mathematics. And we can look really hard, but just as you said, we could always be wrong. Mathematics is a fallible discipline in a different way, but it is still fallible in that sense. And so I just think it's a really fascinating point.
There's a wonderful book by Imre Lakatos called Proofs and Refutations, where he just beautifully goes through one theorem in mathematics and keeps producing counterexamples. So this is a theorem, it's been proved. And he provides a counterexample by playing with the conception of, I think they're polyhedra, sort of what it is to be a polyhedra, and he comes up with these sort of deviant sort of kind of polyhedra that satisfies the definition, strictly speaking, but is not what you'd normally think of as a polyhedra. And so in order to get the theorem to hold, you have to exclude these monsters. He calls this monster barring. So what you do in your theorem, you say, this theorem is a lovely theorem, I want it to hold. And Lakatos has this counterexample, and you say, okay, I have to ban that. So I'm monster barring. And so you ban that by redefining what you mean by polyhedra. And then you come up with another one, and you've got to ban that. And the point of the book is not to sort of undermine mathematics, but rather show that it's not quite starting with these definitions of things. I've got a rigid definition of what a polyhedra is, and then I prove theorems about it, but rather, in part, my definitions are informed by the theorems that I get, and I have to go back and revise. And we were talking about that earlier, but the redefining what we mean by a straight line, right? We do this all the time in mathematics. When we generalize, we redefine things. We usually redefine them in a way that is consistent with the old usage. Okay, you don't want to change it completely, but sometimes not. And this is what this lovely book of Lakatos is about, showing that the definitions are not set in stone. And once you allow that, sometimes the definitions that you choose are motivated by the very theorems that you're supposed to be proving from those. So the order is the other way around. And once you look at it that way, it looks a lot more like empirical science.
Just for listeners, the name of the book again?
Proofs and Refutations. It was actually
Proofs and Refutations. Nice.
It was actually Lakatos's. It's a marvelous book. It was originally his PhD dissertation, and it's written as a dialogue. So and so says, "What about this example?" Then so and so replies this way. So it's written as a sort of Socratic dialogue, which is unbelievably brave thing to do in one's PhD thesis. But
excellent point.
but still, that's what Lakatos did, and this book came out in I can't remember the date, early 70s, but it's I think a greatly overlooked important book. It's a very important book in philosophy of mathematics. Sorry, Ben, I cut you off.
No, it's okay. Yeah, I just want to retrace the steps briefly so that our listeners, because I feel like there's a lot of information. I want to make sure everyone's on the same page. So we sort of started, you noticed this problem, or just this fact that mathematicians prize certain proofs as more explanatory than other proofs. No one can tell us what precisely this means. No one can define this exactly, but there's some proofs that just seem better than other ones insofar as they tell us sort of more about mathematics, or like what's actually going on. And then, so now we're trying to figure out like what is a good mathematical explanation. And so then we go back to the empirical sciences, we ask about explanation there. And then we sort of realize that translating notions of explanation, I mean, first of all, like you said, notions of explanation in the empirical sciences are already fraught and difficult to wrap our head around. But translating these into the realm of mathematics gives problems like immediately. And that, as we saw, trying to grapple with the notion of counterfactual and stuff. And so now it might be nice to go into like some of your work on like intra and extra mathematical explanation and start to like push forward the sort of the positive end of this agenda and like look at what some of the features are of mathematical explanation. But first, just to like ground everything in concrete examples, could you just briefly give an example of like sort of a good mathematical explanation and a bad one, or not necessarily good and bad, but just maybe like a mathematical proof that doesn't have much explanatory content, and then like one that does, just so our readers sort of have some examples in mind?
That's kind of hard to do without a blackboard to
fair enough.
go through a proof. But
fair enough.
The idea here is that certain proofs will just tell you why it's true, and you just kind of have to have done some mathematics to really see this. I gather, we've all done enough mathematics to know that every now and again you sort of follow a proof. It had that phenomenon of just following a proof line by line. You just think, I can see why that follows, I can see why that follows, I can see why that follows, and I can see that must hold, but I'm not getting the big picture, And then suddenly there's a gestalt shift, and you think, now I see. I can remember, for instance, having, as an undergraduate mathematics student, being given a rather big hint by my professor that the proof of such and such a theorem was likely to appear in the exam. So we all studiously worked on this theorem, and I remember just thinking it was about a page and a half, this theorem, the proof of the theorem, and I remember thinking, okay, I'm just going to have to memorize this thing because it's just line by line. So I was just memorizing this thing, but in the process of memorizing it, somewhere along the line, this switch went on, and I thought, I see why this holds now. I don't have to memorize it anymore because I can I can just reproduce the proof now on site. Don't ask me now. I can't even remember the name of the theorem, which says something in itself. But that's a story for a psychology podcast, perhaps. But you have that phenomena of like, now I see it, and it's not just. No. I can picture the whole thing in line by line, but rather you're kind of getting at you understand what's going on. So there's some disagreement in mathematics about which proofs are explanatory and which are not. I had a project a few years ago where we were looking. I wanted some clear examples of this because part of the trouble was that in the philosophy of mathematics literature, we had philosophers of mathematics, me included. Just saying, well, my intuitions tell me this is explanatory and my intuitions tell me this one's not. And I have done some mathematics, but I'm not a mathematician. And I sort of dawned on me that this is a really bad methodology. What I really need here is what mathematicians agree upon as explanatory and not. And I don't want Mickey Mouse examples from high school either. I want real pieces of mathematics. And so we went hunting for some examples of theorems where there were more than one proof, and one proof was generally agreed upon being explanatory and the others were not. Further constraint is the theorem had to be something such that the proofs were understandable to me and my team, who were not mathematicians. So on the one hand, I didn't want Mickey Mouse high school kind of baby stuff, but I didn't want cutting edge stuff that was going to take me 15 years, if ever, to be able to understand it. So we were squeezed from both ends, as it were. And what we found is there was a remarkable amount of disagreement. There's some remarkable agreement on some cases, but there's also quite a bit of disagreement about which proofs are explanatory and which are not. So it's not
interesting. Yeah,
it's not sort of cut and dried, this issue. So it's hard to give unequivocal examples of a proof that's explanatory and one that's not. But you can get the idea. There are such proofs out there, and you do find mathematicians in their less guarded moments, at least, saying things like, this proof is more explanatory than that. Not so much in their papers. This is one of the reasons why this project was difficult, was mathematicians are notoriously good at covering their tracks in their published work. Right? They start off the paper with, consider a function such and such, blah, blah, blah. But whereas philosophers start off with a little story, well, I was thinking about this. You get the kind of intellectual background in a philosophy paper, which annoys the hell out of some people. But I find it helps set the scene for what you're doing. Because mathematicians cut all of that. So they rarely will say something like, I'm going to provide a new proof of such and such theorem, and this one is more explanatory. You almost never find something like that in a mathematics paper. What you need to do is go out to the pub with them and get a few beers into them, and then you can they'll say things like that. So that's one of the things that made this project difficult. That was my first thought. I said, okay, we'll get a bunch of tame mathematicians together, and we'll put some alcohol into them. And then we'll get what they think. And my postdoc said, actually, maybe you can do it by looking at blog sites, because people behave a bit like they're drunk when they're on blog sites. They let their hair down in the right sort of way, And that's, and then in the end, that's what we did. But it is difficult to give sort of clear-cut examples of explanatory, uncontroversial examples, at least, of explanatory versus unexplanatory proofs. And certainly without a blackboard, it's hard to do that. But the idea, I think, is clear enough. And there are such examples out there. Trust me on that.
And just a plug that your book has many such examples. And so listeners who want to see examples can find your work where some of it's written out in great amount of detail.
So you mentioned intra and extra mathematical explanation. So do you want me to say a little about that?
That'd be great, yeah.
Okay, so the distinction between intra and extra mathematical explanation is as follows. So intra mathematical explanations are the ones we've been talking about. It's an explanation of one mathematical fact by appeal to more mathematics. So a theorem that has an explanatory proof, that proof will be an intra mathematical explanation. It's mathematics explaining mathematics. Okay, so that's what we've been talking about so far. Extra mathematical explanation takes us back in a way to the Wigner puzzle of mathematical applications. So it's where you've got some empirical phenomenon that is explained by mathematics, or at least, as I'm inclined to put it sometimes, the mathematics is doing the heavy lifting in the explanation. It seems like the core reason for the event in question is something to do with mathematics rather than causal histories, for instance. And so there, in a way, that's the kind of mathematical explanations I first got interested in for various reasons to do with mathematical realism and anti-realism. But now I'm kind of much more interested in the intra-mathematical explanation, how that works. And that seems much more important for mathematicians. It'd be nice to have an account of intra-mathematical explanation to offer up to mathematicians and see if this makes sense of their intuitions about explanatory proofs. That would be something that was both philosophically interesting but I think useful for mathematicians. The extra mathematical explanation stuff I think ties in with the Wigner problem, and it would be a contribution to understanding how mathematics gets applied. How is it that applied mathematics works? So they're kind of two different things, but tied together by this, having an appropriate theory of explanation.
Interesting. Yeah, I'm curious about how this ties into sort of the realist, anti-realist debates. So I think you mentioned something earlier about when we were talking about the square root of -1, like the reason we can sort of now call this real is because it's useful, because it says things about the world and can be applied in certain ways. Did you mean that? First of all, did you say that? And then second of all, if so, did you mean that in sort of like an instrumental way? Like we have license to call some of this mathematics real insofar as it's instrumentally useful in the world and finds applications?
That's a debate I've engaged in great length throughout my career. I still find it interesting. So I was trying to, when I was talking about the complex numbers, remain neutral on that issue. So thank you for picking me up on that. I was trying to remain neutral. Why should we accept that the complex numbers make sense or whatever? Which is not committing one to believing that they're somewhere, some sense, real or out there or whatever. So-called Platonist view about mathematics is that can be put in a number of different ways, but the usual way is to think of mathematics as being discovered rather than invented. Right. So a Platonist thinks we discover mathematical facts. They're just like empirical facts about the world. We discover these things about the mathematical realm, and they were sitting there waiting for us. They were already true or false, and we had to discover. Or alternatively, you can sort of put it sort of more metaphysically, if you like, in terms of the existence of numbers. So numbers, sets, and functions exist, not exist as in the sense that you can instrumentally use them or whatever, but that they really do exist. There are facts about the numbers. The number 2 exists in some sense. That's the Platonism position. And one of the arguments for this position is that closely related to inference to the best explanation in science. So why do we believe in electrons? Those of us who do believe in electrons, not everybody does, but if those of us who believe in electrons and other scientific posits, the theoretical posits, the stuff that are sort of you can't really get your hands on, and see, they're not observable, these kinds of things, why do you believe in those things? Black holes, gravitational waves, electrons, and so on and so forth. Why do we believe in those? Well, because they are indispensable to our best scientific theories. And so inference to the best explanation says, well, if they're indispensable, in particular to our explanatory practices in our best sciences, then we need to believe in them. So if someone says, for instance, why did, when I rubbed my feet on the carpet, why did I get a little shock? You say, well, that was because of transference of electrons from carpet to feet or vice versa. But there are no electrons, right? Then you haven't offered an explanation at all, right? I'm still none the wiser as to why I got a little electric shock, because you told me this story in terms of electrons and then said, but there are no electrons, right? If that's an explanation, then it requires the existence of electrons. You don't get to explain something in terms of something that doesn't exist. So the basic idea is sometimes called an indispensability argument. If something is indispensable to certain scientific practices, in particular explanatory practices within science, then you are committed to the existence of those things. So for scientific realists, they believe something like this. They think that's why we believe in black holes, that's why we believe in neutron stars, that's why we believe in electrons, that's why we believe in, all of the unobservable parts of our best scientific theories. Not everything. Strings, you might think, kind of that's still in dispute. There are bits of science that are still in dispute. But those bits that are part of established science and are used in explanatory practices within science, you should believe in those. So then, turn to mathematics. There was a great debate about whether mathematics was indispensable to science. Right. It certainly seems that it's indispensable to science. You can't imagine, doing science without mathematics, although there have been noble attempts in that direction. But on the face of it, mathematics looks to be indispensable. But still people want to say, no, well, mathematics is not... Believing in numbers is not like believing in electrons. I mean, numbers are weird. I mean, they're not located in space-time. Don't have causal powers. That's sort of metaphysics in a bad sense, right? So they want to resist that. So they want to say, well, they've got to be indispensable in the right sort of way. It's not just indispensable to science. For instance, you might think frictionless planes are indispensable to pedagogical practices in science. If you want to explain the law of inertia to first-year physics students, give them an ice rink and then say, imagine a frictionless plane, which is a bit like this, but only less friction, right?
Right.
So you might need frictionless planes for pedagogical purposes. And they're indispensable. Let's suppose you cannot explain inertia without appeal to frictionless planes. Mm-hmm. You still don't want to say, well, that means frictionless planes exist. We just haven't found any, but they must be out there. Right, you want to say, no, there are no frictionless planes. It's just a pedagogical device, indispensable though it may be. So the debate then turned to in what ways are things indispensable? Because just being indispensable doesn't seem enough to warrant realism about the entities in question. And one way in which this style of argument does seem to run quite nicely is if you think that it's indispensable to explanatory practices, hence the connection with inference to the best explanation. So if you believe that inference to the best explanation is a good inferential pattern, if this thing helps explain stuff that I know is going on, certain events, and I need electrons in order to explain that, then damn it, you need to believe in electrons. Mm-hmm. Right? That's an explanatory indispensability argument. Mm-hmm. So then people start to think, well, can mathematics play that kind of indispensable role? Can mathematics play this explanatory role in science? And those of us who got interested in this started coming up with some examples of mathematics where it apparently is playing some kind of indispensable explanatory role, and thereby licensing Platonism, realism about the mathematical entities. That's all, of course, highly controversial. I have my views about this, but that's the dialectic, at least. So there are those of us who are trying to think of examples where mathematics plays this explanatory role, and there are those on the other side who don't believe in mathematics, who've got to come up with an alternative story about these cases, or deny that they're explanatory, for instance.
Mm-hmm. Yeah, nice. One example from your book that I found fantastic was the beehive example, where so I guess bees construct the inside of their nests using certain hexagonal patterns, and the explanation, at the moment, our best explanation as to why they build it in such a way is because of the mathematical properties of these hexagons. They fill the space in some optimal way. And thereby, with a finite number of resources, sort of allow the bees to make the best use of a minimal amount of space. And so I guess this is both an example of an extra mathematical explanation, because you're explaining something in the physical world with math. But then this is also an example of where we'd appeal to the reality of mathematics. But in this case, what exactly are we arguing the reality of? Is it all of geometry? Is it just the theorem which says that these patterns are sort of the most optimal, have the most optimal space filling properties in this sense? What exactly we're arguing is real there?
Yeah, good question. So this is supposed to be an example of an extra mathematical explanation. It was actually conjectured, I think, by Darwin originally. Darwin noticed this pattern amongst beehive, about the structure of beehives and this consistent hexagonal structure, and conjectured quite insightfully that there must be some optimality result in the vicinity, and said, I don't know enough mathematics to know what that would be. And it was only relatively recently proven. It was called the honeycomb conjecture for a long time, now the honeycomb theorem, which proves that if you have the following assumptions, that wax is expensive for bees, so they want to minimize the use of wax. They want to maximize the area of the volume of storage, and they need to have access from one end. And you don't want to waste space. So it's kind of little cylinders, for instance, would work to some extent, but you've got all that wasted space. Anyway, you can prove the result is that the hexagonal structure is the right one. What does that tell us about mathematical realism? Well, that's just an example of where mathematics is playing an explanatory role in science. So anyone who wants to say mathematics can never play that role needs to tell me what's really going on in this case. Okay, so which bit of mathematics does it give me reason to believe in? Well, whatever mathematics it takes to prove the theorem. Quite a bit of calculus, and so on and so forth. I haven't been through the proof myself. I'm not quite sure exactly what's involved there, but I presume that's going to be a standard sort of operations research kind of problem, an optimization problem. So there'll be a fair bit of calculus and the like there.
Right.
So it licenses belief in all of that. But the point of that example was more just those who want to say that there's no sense in which mathematics can offer an explanation in empirical science. Mathematics is just kind of handmaiden to the science in question, and the real explanations live in this case, the biology. It's something to do with the bees. This is about bees and beehives, and it's got to be about something to do with the relevant biology. The point of this example is to say, if you leave that theorem out of it, you haven't got an explanation. There's no amount of stories about the biology that will give you this, that will fully explain why you see this recurring hexagonal structure. At least part of the explanation must involve the relevant theorem. And indeed, going right back to Darwin saw that. Darwin didn't know the theorem, but conjectured that there must be some result because the biology requires there to be such a result for this to be explicable at all. So that was really the point of that example, was to show that, just to sort of soften the reader up, if you like, look, here's a kind of case where it looks like math. This is the kind of thing I'm thinking about where mathematics might play an explanatory role. I don't think that example in itself wins the day, but it's more of a kind of, as I said, a softening up approach.
Nice. It softened me up, so
okay.
Mission successful.
So I want to pivot the conversation to some other areas of your work that are both personally interesting to me, but also touch on things we just happened to talk about on the podcast recently. So the two domains are both logic and also thought experiments, and the role of, say, thought experiments and toy models in legal reasoning, because you've been thinking about that recently. So let's start with the first, the subject of logic. So I've only learned recently that there isn't just one logic. There are multiple sets of logic, and Spock misled us all, right?
It's not logical, Captain.
Exactly.
It's only one.
Yes. But so when I learned that from your work, I was trying to figure out why that kind of surprised me, and I think part of it is due to the conflation of logic and of the notion of truth. So I don't think that people want to say that there are multiple ways you can define true and false. And that seems like that's a fairly static category, but there are multiple logics. And so one in particular we've been that I wanted to ask you about is para-consistent logic. Did I get that correct, first of all? And so to set it up a little bit, if you could talk about what logic is, what its relationship is to truth, and why there is a role for alternative logics in various domains of inquiry. Okay,
have you got 6 months?
It'll be a multi-part episode.
This is
carve off a chunk of it.
This is a big question. There's a logic. Again, really big question, but quick stab at that. It's a theory of what follows from what. It's about logical consequence. And you usually set aside a certain kind of what follows from what, for instance, statistical what follows from what. Okay? So if I'm doing some scientific experiment, and I've got my, I've confirmed the hypothesis, I've got suitable power, I've got suitable sample sizes and the like, I can say I've confirmed the hypothesis. But I've not confirmed the hypothesis infallibly, right? It's only statistical. Even if every swan I've ever seen is white and I've seen lots and lots of them, there's still the existence of black swans out there, and they're always possible. So we set aside the statistical notion, which is a great deal of our reasoning, I should say. A huge amount of our reasoning is statistical in this sort of way. So by setting it aside, I'm already setting aside a huge amount of what we think of as consequence. But for a logician, logical consequence is what follows from what, with no exceptions, right? So I'm not thinking about the statistical sense. So that's to do with probability theory and statistics more generally. So when we say something, canonical examples, if A, then B, indeed A, therefore B. Okay, modus ponens. That's a valid argument. There are no counterexamples to that. Well, I should qualify everything I say because we're talking about philosophy here, but on the face of it, there are no counterexamples to that, right? If the conditional, if A then B, if that's true, and A is indeed true, then that guarantees the truth of B, right? So think of logic about the study of truth preservation. Okay, so there's debate about exactly what logic is, but that's a first stab at a reasonable definition of logic. It's the theory of logical consequence, where logical consequence is this truth preservation. In classical logic, you have just two truth values, true and false, right? And first question, why? Why only two? Why not half true? Why not neither true nor false? Why not entertain degrees of truth, right? So, for instance, fuzzy logics introduce uncountably many truth values. So instead of just having one which we identify with true and zero which we identify as false, for the computer-minded people, that's the standard story of, we use zero and one. 0 is false, 1 is true. Let's have the whole interval, all of those values between 0 and 1 as well, right? And it turns out that that's incredibly useful for all sorts of purposes, from solving puzzles in philosophy to making your fridge more efficient, your refrigerator more efficient, right? Fuzzy logics are useful for all sorts of things. But what you're doing with a fuzzy logic is you're introducing more than the two truth values for various reasons. But we don't have to go all the way to that. We can just think of, why not have a third value that is thought of as half true, or think of that third value as not the other two, right? And again, if you think about this, is not crazy talk. If it's misty sort of weather where you're getting a little bit damp by being outside, but there doesn't seem to be actual rain falling. Then someone says, is it true that it's raining? You want to say, no, it's not true that it's raining. Is it true that it's not raining? No, it's not that either. It's sort of neither true nor false. There's lots of, or yes and no, it's right. There's lots of places where you want to give an in-between answer to something. Someone who's of medium height, and you say, is it true that they're tall? You say, no, it's not true that they're tall because they're medium height. Is it true that they're not tall? No, because that sort of suggests that they're short. They're not short, they're medium height. So it's neither true nor false that they're tall. That sits very well with, everyday usage. So introducing a third truth value, the not the other two, not true and not false, very, very natural kind of move. I can motivate it from all different directions. Think about fiction. If you think of a piece of fiction, what's stated in the fiction and what's implied from what's stated in the fiction is true, And what's stated in the fiction as being false and what's implied by what's stated in the fiction as false is false. But what about the rest of it? You know, how many pairs of socks does Harry Potter own? Right? I'm no Harry Potter scholar, but I take it that that's not stipulated in the story because the story has more interesting things to talk about. So to say Harry Potter has 17 pairs of socks, true or false? You want to say neither, right? Surely that's the right answer. It's kind of crazy to think that there is, yes, fact of the matter about this. So all different ways to motivate so-called non-classical logics. In particular, one that just introduces a neither category for true and false. Not true, false, and neither. And there are systems that have been around for 100 years or so, at least, playing with those sorts of ideas. So these find applications, both in philosophy and in all sorts of computing applications, for instance. So the move to non-classical logics, I think, is interesting and well motivated. Mm-hmm. The so-called paraconsistent logics, these are logics that address a particular problem with classical logic. And again, this is very common in philosophy of logic. You look at classical logic as your starting point and you notice that there are problems. So, for instance, classical logic has problems when it comes to various so-called vague predicates like tall and the like. You get these Sorites arguments, or it's kind of a slippery slope argument. They seem problematic for classical logic, so that motivates a push to something like a fuzzy logic, for instance, or just a three-valued logic where you can deny the truth and the falsity, neither true nor false. So you start with some problems with classical logic and you try and fix them by moving to something that's non-classical. And it might be that you think this new logic is the one true logic, so you're still there with Spock, right? There is one true logic, it's not logical, Captain, and what I mean by logical is this new logic. Or you might just think, for these sorts of purposes, I need this kind of logic, right? Or for that purpose, I need another kind of logic. And there are many, many different logics. Paraconsistent logics address a particular problem with classical logic, and that's the following: that if you've got a contradiction, any arbitrary proposition validly follows from that, right? And you can prove in 5 lines that you tell me what you would like me to prove, and I can prove it in 5 lines if I'm granted a contradictory premise. Now, to be fair, defenders of classical logic will say, well, that just shows you how bad contradictory premises are, right? There are no true contradictions, so we never have to worry about that. Go back to our discussion about inconsistent mathematics, okay? A little-known theorem of naive set theory is that the moon is made of green cheese. You could prove that validly in 5 lines from naive set theory. Now, of course, naive set theory you want to say is not true, it was inconsistent, but given that you believed it to be true at the time, there's a 5-line proof that the moon is made of green cheese. A theorem of mathematics that the moon is made of green cheese. That's bad, right? So, paraconsistent logic is one that simply does not allow you to derive any arbitrary proposition from a contradiction. So one way to think of paraconsistent logics is if you think you might have inconsistencies in your system, then a paraconsistent logic can be thought of as a nice insurance policy. Right? It just stops explosion, as it's called, the proof of absolutely everything from a contradiction. So lots of applications for this, nothing to do with philosophy, just, we three are putting data into a data set. We're just doing mundane data entry, and we know that there could be some typos. We know that we could be entering inconsistent data. You put in one thing because you believe it to be true. I put in something else because I believe it to be true. And now we've got an inconsistency in our data set. And suppose we're now going to use some AI techniques to derive things from that data set, some data mining, we don't want it telling us that the moon is made of green cheese, right? But yet that's formally derivable from this inconsistent data set. So to stop that, or to make that harder to arrive at least, you might think a paraconsistent logic is applicable here. So paraconsistent logic is just one such that not everything follows from a contradiction. And doesn't say contradictions are true or anything like that, just that if you do have a contradiction, you can't prove an arbitrary proposition from that.
It contains the explosion, so to
yes,
speak. So that the explosion. Yeah. That's great. Yeah.
And they might motivate that by other reasons. So people think, for instance, classical logic has, apart from contradictions, has problems elsewhere, just problems to do with relevance, because all it does is tells you that if the premises are true, then the conclusion is true. But you might think that the conclusion's in some sense got to be relevant to the premises. It's got to be true because of the truth of the premises, not just because they happen to be true, right? You want some notion of relevance, that the premises guarantee the truth of the conclusion because they're on the same topic or something like that. You want some notion that it's the premises that make it true, not just that if they happen to be true, then this also happens to be true, right? You want something to do with the way that the premises and the conclusion interact. And that's not written into classical logic. That's just not part of the story. So again, that pushes you in the direction of so-called relevance logics, which ask for some extra thing, which is that the premises and the conclusions have something to do with one another. There's a technical notion of relevance here. So these are just some of the various logics that are around. They have applications. They're motivated by and large by shortcomings of some other logic, namely classical logic. And then question arises about what your attitude to these other logics should be. And one bit can be just kind of pragmatic. Okay, there's lots of logics. Anyone who denies that there's lots of logics is just mistaken. Okay, there simply are lots of logics as technical kind of, technical systems. Yeah. The question is there still just one true logic? And what we're trying to decide now, which of these many logics we have is the one true one? Or is it a kind of horses for courses, right? Use whatever suits you best at the particular time. And so if that's right, then Spock was wrong to be saying it's not logical, Captain. What he should be saying is, it's not logical under these circumstances to be using that particular or something. He needs to sort of be a little bit more particular about it. Mm-hmm. And that's an interesting and I think a live debate in logic circles about what our attitudes to these non-classical logics should be.
I get so uncomfortable thinking about paraconsistent logic as it relates to mathematical explanation. So, something like, I think the proof that everyone's taught that like the square root of 2 is irrational goes something like, assume it's rational, write it as a fraction, as a minimal fraction, and then basically you just derive a contradiction in a few more steps. And then you say, okay, we arrived at a contradiction, and so our premise is refuted and it's actually irrational. So if you now apply like paraconsistent logic, it seems like you couldn't get away with saying it. Your original premise could be false, but that doesn't mean the negation of that premise is true. So it seems like if you were to apply something like a paraconsistent logic to a lot of math, you would lose a lot of the results, at least those results that are proved by either proving the contrapositive or something. So how does that relate?
I think that's an issue for other kinds of logic. A paraconsistent logic is just one that does not allow you to derive an arbitrary proposition from a contradiction. But what you're worried there about is double negation elimination, right? So you start by saying, I want to prove P, so I assume not P. And then I derive a contradiction, so I conclude that my starting premise, which was not P, is mistaken. So I conclude not P.
Right.
And then double negation elimination says that's the same thing as P. So I've proven P. Right. That's the form of proof by contradiction. The problem that some people see with that is in the double negation elimination step, the final step of the proof. And so in particular, in intuitionistic logic, and this was a serious debate that arose in mathematics early in the 20th century, the great mathematician Brouwer, for instance, advocated for so-called intuitionistic logic, where, amongst other things, proof by contradiction is not a proof. Right, you've got to prove the positive case. You can't prove it by this. All that you prove in a proof by contradiction is you prove that not P, but you haven't proven P yet. Right. You've got to, because
Yikes.
Negation behaves a little differently in intuitionistic logic. And this was a serious debate that rose out of mathematics. And there's still mathematicians around now who still think that intuitionistic logic is the appropriate logic for mathematics. And mathematics, to some extent, has run off the rails by just assuming that double negation elimination holds. So that's a separate issue. That's another non-classical logic. But there are those who will defend that. It does severely limit what you can do, or at least forces you to find other proofs, right? So stops you from, they would say, stops you from being lazy and just saying, I want to prove P, so I'm going to assume not P, which is kind of a, undergraduate mathematician's first move, right? That was certainly when I was give me an assignment question to prove P, my first assumption will always be not P. It was my go-to style of proof, right? And rather than trying to prove constructively, So, for instance, think about existence proofs, where you can prove that there exists a function such that so on and so forth. One way to do that is to produce the function. Here it is. I specify it. The other is to say, if there weren't such a function, then a contradiction would arise. But you got no idea. If you do it by proof by contradiction, you got no idea what the properties of that function are like, except that were there not to be such a function, there would be a contradiction. So the constructive proof is valued, and even by mathematicians who are not intuitionists about this, those who actually subscribe to classical mathematics, still think that the constructive proof is enlightening in this kind of way. So anyway, that's a different issue. I think that the rejection of proof by contradiction, proof by non-constructive, rejection of non-constructive proofs more generally, that's an issue that arose mostly out of the debates about intuitionistic versus classical logic in mathematics. But I don't think that's I think the issues to do with paraconsistency are separate.
Just so being mindful of your time, I want to move the conversation to the subject of thought experiments and their uses and misuses, and in particular in the context of legal reasoning. So the reason I bring up the thought experiment thing is only because Ben and I were in an argument about this in the previous podcast, and we made very little progress. But the subject was just what is the role of thought experiment in argumentation, and in what utility do they have, what utility do they not have, where can they get us into trouble, etc. And it was shortly before that I watched your YouTube talk, which we'll link to in the show notes, talking about the role of toy statistical models in legal reasoning. And so I would just love to hear your thoughts about that domain, and take it where you will.
Sure. So thought experiments are often thought to be the kind of bread and butter of philosophy, whereas scientists are doing real experiments, philosophers just mess around with thought experiments. And there's an element of truth to that. Thought experiments do play an important role in philosophy, but they also play an important role in science. So famously, Einstein's thought experiments about travelling on a beam of light and what the clock would look like if you were travelling on the beam of light. So there are thought experiments in science. Galileo's famous thought experiments about dropping two rocks from a cliff tied together, right? You know this thought experiment, right? refutation of Aristotelian physics by pure thought experiment. Brilliant thought experiments. But like real experiments, I think thought experiments need to be carefully constructed and make sure you're isolating the hypothesis in question, if you can ever do such a thing. But the problem is that you might be introducing confounders in a real experiment. You might be thinking you're testing this, but you're in fact other things are going on, right? And you need to be careful to isolate as best you can the core hypothesis. And so while I'm not against the use of thought experiments in philosophy or in science, it's just that you've got to be very, very careful that what you're doing is indeed isolating. Just as in a real experiment, you're isolating the hypothesis in question, and there are not alternative explanations for one's intuitions. So for those who don't know what a thought experiment, I take a thought experiment to be something like, imagine such and such a case, and clearly this would be what would follow from that. So in the legal reasoning cases, the thought experiments I'm most interested in here are those about the use of statistics in the courtroom. So you have a thought experiment where you have only statistical evidence for a crime or for or for a liability claim or whatever. And you only have the statistical evidence. So you construct a thought experiment that's supposed to isolate that and that only. So one of the classic examples is a liability case where there are two bus companies in the town, the red company and the blue company, and there's an accident involving a bus, and someone wants to seek compensation for the accident, and they know that it was a bus. They don't know anything about the colour of the bus. They're either colourblind or it's night, or fanciful stories about why you don't have anything to do with any knowledge of the colour of the bus. And the only evidence you have is you know that it was a bus, and that, make up the figures you like, but something like 80% of the buses in town are the red bus company and 20% are the blue bus company. So you sue the red bus company, and intuition is supposed to say, no, that would not be fair because you're just relying on the statistical frequency of the red buses on the road versus the blue buses on the road. There's no evidence that it was in fact a red bus involved in the accident. So that's the kind of thought experiment that people appeal to show that there's something, if not defective, about statistical evidence in legal settings, but at least something more needs to be said. Statistical evidence is not enough on its own, is the way some people inclined to think of it. And these thought experiments, there are a number of them. I won't go into the others, but that's kind of typical of these thought experiments. You just try and isolate everything and show that all you've got, by stipulation, is just the statistical evidence, and most people are inclined to say that would not be enough in this case.
If I could just ask a clarifying question. So the claim is that people are using statistical evidence in court cases all around the world all of the time. And this is problematic. And to try to make the case that it's problematic, you come up with the red and blue bus company thought experiment. And so what's the takeaway? Because I find that thought experiment to be quite persuasive. But what do I do with that? Do we just disallow statistical reasoning in court decisions, or I guess what are the practical? What is the practical relevance, and what are we doing as a society that we perhaps should not be doing, or vice versa?
Yeah, good question. I think the law is rather undecided on how it should treat statistical evidence. It varies a little from country to country, I would imagine. I've not done the work on that. Mm-hmm. But certainly within a given legal system, you'll find rulings against statistical evidence, and you'll find rulings for. And it's difficult to get clear advice from the law itself about it. It has a an uncomfortable relationship with statistical evidence, shall we say. So a number of really well-known legal scholars have written pieces arguing against it. You find significant figures writing for it. Legal findings have been torn on these cases. You'll find precedents on both sides here. And so part of what I think people are trying to do is to settle this question, because it's not like, yes, statistics are used widely in the courtroom, so we're trying to overturn all of legal practice or something like that. It's that the legal practices are unclear about what they should be doing here. And so it's trying to help guide legal practice and nudge it in the right direction. So that's the way I see it, at least. Maybe that's a little simplified, but I do think that the people engaged in the debate on both sides have their hearts in the right place. I think law really does not know what to do with legal evidence. On the one hand, it looks like it does, because there are clear cases where all sorts of complicated statistical evidence is used in the law, but there are some pretty well-known cases where this evidence has been rejected, and rejected because it is purely probabilistic. So these thought experiments are trying to get at the heart of what the problem is. What is it that's wrong with this? Like, why did it get passed in this case and not in this other case? Well, you might find that, well, in the cases where it was okay, there's something else going on in that case. It was a different kind of probabilistic evidence to this one or whatever. So if you've got nothing other than pure frequency data, which is what you've got in the bus case, pure frequency data is not enough. Let's suppose that's the take-home message from that. To be upfront, I don't buy that. I don't think that's right. But you might think that the people sort of pushing these sort of examples, that's what they're trying to, that's a working hypothesis. Pure frequency data is not enough, but frequency data might be used to bolster other sorts of evidence or vice versa, but you can use frequency data in the courtroom, but not just on its own. That would be sort of an interesting and plausible, to be fair, take on this. So that's what the thought experiment is supposed to do. Why am I suspicious of them? Well, I don't think it isolates the pure frequency. I think there's lots of things going on in that example. What you're doing, for instance, is just stipulating away things that I think you have no right to stipulate away. For instance, that you're absolutely certain that it was a bus and you've got no idea what colour it was. I mean, if you're that blind maybe it was a truck. Maybe it was a minivan. I mean, really, the absolute certainty about being a bus? Surely there's just a little bit of doubt about whether it was a bus. That's all I require. Just, normally when we say, yes, I saw an accident and it was involved two cars, I could be wrong. Maybe one of the cars was in fact a minivan. I'm not completely certain.
And you can't call the bus company. You can't check their route.
Yeah.
So all of these real world details are just stripped from the thought experiment in such a way that it is claiming to be, I guess, leading, but is misleading, or it is unintentionally misleading, because the very thing that it is isolating, by trying to isolate it, it removes all of the factors which would be relevant in a real case, in a real statistical.
Yeah, that's right. So you've got things that you would normally do. So, for instance, you just say 80% of the buses are red, 20% are blue. Then reasonable question is, what about on this particular route, right? Bus timetables are free. You can get this information for free. I would like to know what the frequency data for this particular route is at that particular time. It might still be that the red bus company comes out looking more liable than the blue bus company. But why would you deprive yourself of that information when it's freely available? So what you do with the thought experiment is you make these really quite unreasonable assumptions. So, for instance, implicit in the thought experiment, it's not usually put this way, but implicit in the thought experiment is that buses run randomly through this town. There are no routes, there are no timetables. right? Or if there are, you're not allowed to look at them. Why aren't I allowed to look at them? Right? That would help, right? And if there are no such things, then these buses are just running randomly. So I'm supposed to imagine a town where there are 80% of the buses are red and 20% are blue, and they run randomly all day long through... I'm losing a grip on this. Right? So what most people don't think of it this way, but what you're being asked to imagine is something really, really difficult. And no wonder they have pause about assigning liability, because they're having trouble getting a grip on the case, let alone anything else. And so they say, no, I wouldn't assign liability there. But if you fill in some of the details, you're still isolating the statistical stuff. So let's say, okay, they're not random bus companies. That's kind of crazy. They do run to timetables. We've got the timetables. And at that time of the day, 80% of the buses running down that street are red and 20% are blue. Would you assign liability now? Yes, I would. I don't see any problem there. And I think people's intuitions can be pushed around a little bit by filling in some of the details. And so at least some of the intuition to resist these cases, I think, is because of what you're being asked to imagine. And it sounds perfectly fine on the face of it, but in fact you've been asked to imagine something really quite unrealistic. There's no uncertainty about the participants in the accident. The buses are running randomly. There are no timetables. There are no known clusters of buses. So even amongst randomly running buses, you can still have clusters here and there. And there's no information about that at all. You're completely ignorant. And there's a very good sort of piece of advice you might think. If you're completely ignorant about something, don't make a judgment, right? Be cautious. Maybe that's what's going on here. Doesn't sound, you say the thought experiment, in a nice calm tone, and it sounds like you're giving the person lots of information. But, they're kind of realising they haven't got enough information here, and so a little, principle of caution kicks in, and they say, no, I won't assign liabilities in this case. I think that's perfectly fine. Fill in some of the details. Do they still want to not assign liabilities? To be fair, I think a lot of people still, once you start filling in bus timetables and the like, they still do want to say, I resist assigning liabilities. But not me. I'm actually happy with statistical evidence, and I think, particularly when you're talking about a liability case, it might be different if it was a criminal case, but that's because the standards of proof are higher. 80% is not nearly enough for a criminal liability in my book. But that's now that's a different issue. Now that's not about probabilistic evidence or not. That's about getting it at a suitable standard, right? So what the construction of these thought experiments, the way the construction works is you say, give me a standard of evidence, and in civil cases it's preponderance of evidence, which is just more likely than not. So presumably 50% probability is the relevant standard there. So you just jump way above that, 70%, 80%, whatever, of the buses are red versus blue. And so it can't be the standard of evidence you're quibbling about when you resist liability here, because we've stipulated that it's high enough for that. So it must be that you don't like statistical evidence. That's the sort of line whereas what I want to say is, no, you're being asked to imagine something quite unrealistic. It'd be perfectly reasonable for someone to say, I don't know enough in this case. Not because statistical evidence in itself is not enough, but there's more statistical evidence I could have, and I could have it for free. Why would you deny me free information? And if you say that free information is not available, now you're committing me to something like, buses running randomly through a town with no timetables or routes. That's difficult. So that's my suspicion of these thought experiments. I think most of them are constructed in such a way to show that statistical evidence is questionable in the courtroom. And I think in all of the examples that I'm aware of, there are other things to explain people's intuitions that has nothing to do with the statistical evidence itself.
So I would imagine that most of our listeners don't find themselves in a courtroom being presented with a thought experiment that is meant to discredit the use of statistical reasoning. But I would imagine that most of our listeners do hear thought experiments regularly, just throughout their day-to-day, throughout their life. And especially in the moral domain, this tends to be invoked quite often, say with like Peter Singer's Shallow Pond example. And maybe just to try to leave the listeners with some useful heuristics when they hear these kinds of thought experiments. Do you have any recommendations, or like how should we think about a thought experiment when it's presented to us? Because as you said, it's all often presented in this very calm, reasonable, rational way, and there can be some duplicity happening, unintentional, of course, but where the relevant details are actually being hidden from view. And so I guess I'm just wondering if you have any recommendations or any cognitive tools that you use when invoking thought experiments or when hearing them for the first time.
I wish I did. That would be nice to have some heuristics here. I guess I tend to be a little cautious about such things, and so, I mean, that's what philosophers are. We're counterexample finders. Give me a thesis and let me treat it suspiciously and try and think of a way that might be false. So when I'm presented with a thought experiment, I start immediately thinking, what's driving this? If I do have the intuition, and the most worrying cases, I think, is when you have a particular horse in a race, and like, I have my views about such and such, and someone says, well, let me give you a thought experiment to show you why that's wrong. In part because I've already committed to some position, I'll be suspicious of that thought experiment, especially if I have the intuition in question. So I think, that's bad. I've got the intuition that goes against my own view. I could change my view about this thing, and that has indeed happened for, I think, most philosophers at some stage. You've thought something, you've been convinced by argument or by thought experiments that it can't be right, and you change your view. That can happen. But particularly when you're kind of invested in a view, you're inclined to think about the thought experiment a little more carefully and think, could there be something else going on here? And indeed, that's what's going on in this particular case. I am a card-carrying, probabilist. I think that probability theory lies at the heart of so much of our reasoning, and we must be able to make sense of it. And in one of the most important settings where we do engage in this kind of reasoning, the courtroom, that you would be banning statistical evidence there, that just seems to me like the worst possible outcome. That's where we need to be really careful about our statistical evidence, make sure we're not being misled by it, make sure it's being done properly, and so on and so forth. But that's where the action is in places like courtrooms. So I think in the courtroom you want your best reasoning on show, and so I'm fully committed to using probabilistic evidence there. So when I'm presented with an example that shows that probabilistic evidence is suspicious, I think, okay, what's going on in this particular case? Why am I supposed to have this intuition? Sometimes I just don't have the intuition, and that's partly because of being a card-carrying probabilist about all of these things. But in the cases where I do have something of an intuition in the direction that I'm supposed to, I tend to just look at the thought experiment and critically engage with it. And not to say that I can always pick fault with it. I mean, that would be somehow dishonest, right? I believe this position, and so any thought experiment to the contrary must be, I'm not suggesting that. But just treat thought experiments somewhat suspiciously, in much the same way as you should treat real experiments suspiciously, right? Was the sample size large enough? What was the power of the experiment? Was the hypothesis that they claimed they tested really the only hypothesis that could be going on? In the psychology research, for instance, did the participant systematically misunderstand the instructions or the questions that they're being asked? They're given vignettes. What would you say in this particular case? Did they fully understand them in the same way as the experiments did? These are all important questions for any experimenter to engage with. And there are good experimental psychologists and there are not so good experimental psychologists. And we all need to sort of aim for the good end. And I think with thought experiments, it's not a matter of just, oh, here's a thought experiment, but is it a good one? There's no kind of equivalent to power and the other things, sample size, but you can make sure that you're isolating or close enough isolating the hypothesis in question. And I think I don't want to make general claims about thought experiments everywhere, but certainly these ones in the legal setting to do with statistical evidence, I think they all fail to isolate the hypothesis in question that they claim. Which is not to say that therefore legal evidence is fine, if statistical evidence in the courtroom is fine. It's just that maybe you need to come up with better thought experiments. And maybe there are such thought experiments that would even convince the likes of me. Great, let's see them. But the bus one just don't cut it for me.
That was fantastic. I feel like my thinking has a lot of room to evolve on this front. My intuitions keep jumping back and forth even as you're talking. Yes, I'm convinced. No, I'm not convinced. So, and it seems pretty important. I mean, even the language of just like beyond a reasonable doubt invokes a certain notion of probability. So being able to grapple with that and understand precisely what we mean by those kind of statements seems important. So anyway, I look forward to seeing your next few papers on the topic. That'll be exciting. Yeah.
Well, we got interested in this actually with a real case, and perhaps I could just say a bit about that. So it was an actual a case
That'd be wonderful.
Where statistical evidence was on trial in many ways. So it was a case of a drug smuggler smuggling heroin into John F. Kennedy Airport during the 90s sometime, I think it was. And the guilt was unquestionable. The guy was caught with the drugs. And the question was, what was the quantity of drugs he was caught with? And even that's statistical, surprising. This surprised me when we looked into the details of this case. Even estimating the quantity of drugs that someone has is a statistical matter, because this was heroin, and the heroin is mixed with some paste, and the sentencing is based on the quantity of heroin, not heroin plus paste. So they need to extract the heroin from this mixture and charge them with the amount of heroin that they in fact have. And this guy had something like swallowed 103 balloons of this heroin paste mix.
Holy smokes.
And so they had to sample the 103.
Right.
And the extraction process takes some time. So in the end, I think they only got a quantity for 3 or 4 of the balloons and then extrapolated from there. So it's already statistical through and through, right? Mm-hmm. That surprised me. I kind of thought if someone's caught with heroin, you just put the damn thing on,
count the heroin.
put the bag on a scale, right? I'm very naive about these things. So, but then the extraordinary move came where the sentencing is based on the total quantity of heroin smuggled into the country, and it's ambiguous between total quantity across your lifetime and the total quantity on this particular trip that you were found guilty of. And it had always been assumed that if you're charged with heroin smuggling now, then the quantity that you should be sentenced based on should be that quantity, right? But for the first time in US legal history, they interpreted it as what's the quantity this guy has smuggled across his lifetime. And so they made estimates of the number of drug smuggling trips this guy had made, and then multiplied the quantity from this trip by the total number of trips. And so they came up with a figure that involved a rather lengthy sentence, as you can imagine. And that was then rejected was appealed, and that sentence, not the guilty verdict, but the sentence itself, was overturned by the Second Circuit Court. And the reason they gave was that it had only been established statistically that this was the quantity of drugs he smuggled. The actual quantity found on him was a different figure. So it looked like there was a rejection of the statistics in question, And then this debate sort of arose in both legal scholarship, in the scholarship circles, but also between the district court and the Second Circuit. There seemed to be a disagreement between the judges about the validity of the statistical evidence. Not strictly speaking on that statistical evidence, because multiplying by the number of trips is very bad statistics, right? So that's another confounder here. You're comparing bad statistics with something else, right? So they then redid the statistics and used a fancy bootstrapping method to get an estimate of the quantity of drugs. And again, it was rejected by the Second Circuit. And so many people said, oh, this is terrible, this is terrible. This amounts to the wholesale of rejection of statistical evidence in the courtroom. Very bad. And a couple of colleagues and I sort of dragged into this debate. And one of the things that we found interesting about it was that our intuitions were that the Second Circuit got it right. This guy should be charged with the quantity of drugs he was caught with and not based on the other trips, or at least it was over, his sentence was longer than it should be. So we had considerable sympathy with the Second Circuit. But on the face of it, the Second Circuit was rejecting the statistical evidence and the district court was accepting it. And we were all either statisticians, one a statistician, a mathematician, and a philosopher. Sounds like the beginning of a joke, right? Walked into a bar.
Yeah, I was going to say. Well, you need the 800 bags of heroin. So.
But, we were all, statistically minded and thought statistical evidence does play a big role and should play a big role in the courtroom. And yet our intuitions were kind of siding with the anti-statistics side of things. So we were, our early discussions on this is, what the hell's going on here? Why aren't we kind of clearly on the side of the district court? So our first paper on this was trying to, articulate to ourselves as much as anything else why, in fact, the district court did get it right, and they got it right on statistical grounds. There are good statistical reasons to be suspicious of the particular statistics in this case, but it's not a wholesale rejection of statistics. And I found that a useful exercise, but it was motivated by a real-world example where, again, it's not the statistics that was isolated. There was questions about the validity of the statistics, and that's what was confounding my thinking initially on this. And so I've carried that same line of thought over to thought experiments. Okay, in thought experiments, are you really being driven by the thing that you're supposed to be driven by, or is it something else, like confusion about the case itself, or other kinds of uncertainty that you've told to ignore but you just can't, for instance?
Excellent. That was so fascinating. Yeah. And I just want to thank you for coming on and for enlightening us, both in this conversation, but just in your work and in your writing in general, to the importance of the philosophy of mathematics and thinking carefully about all sorts of domains that I had not thought carefully about before reading your work, like logic and the role of statistical reasoning in the courtroom. So thank you so much.
My pleasure. Great talking to you.
Yeah, that's great. Well, thanks again. Cheers.